Hello, thank you for joining us. We are Anunnaki Instruments from the UTSA College of Electrical and Computer Engineering. We are here to present to you the hands-free Electrolarynx, sponsored by Romit. My name is Matthew Callahan. I am the project manager. I am studying computer engineering.
Howdy, my name is Juan Gomez. I'm the project documenter, and I am studying computer engineering.
My name is Christian Lopez. I'm the project liaison, and my major is computer engineering. This project is being sponsored by the Romit Company, located here in San Antonio. Romit Company currently develops a device known as the Electrolarynx, which is a small handheld device that uses a buzzing motor to create an artificial voice for people who no longer have vocal cords or those affected by muscle paralysis brought on by conditions such as strokes. The current company president, Tom Dodson, brought the project to the attention of the UTSA ECE department in hopes of improving upon the existing device by making it hands-free to improve user experience.
Our design team came up with a few ways to improve the device through a rigorous process of weighting concept ideas against each other. We decided the best ways to improve the Electrolarynx were to make it hands-free, being wearable around the neck with the buzzing motor pressed firmly to the throat. We added motion sensor technology to automate the device's buzzing operation, with an accelerometer output being used to determine if the motor turns on or off. We also added a microphone to record voice audio, and alongside that we developed a Bluetooth Classic on the microcontroller in order to pair with and transmit the user's voice to their modern devices, such as phones and speakers.
Our schedule consists of many dependent tasks and some smaller, more independent tasks. The beginning stages mostly involved ordering parts, creating a model for our neck unit, and finding a chip for our microcontroller. Once we had our parts, we began developing our proof of concept. This stage involved building breadboard circuits and writing software modules. As soon as all of the software modules were complete, we began combining them to confirm that they all worked properly together. Finally, we had to fit all of our components inside the casing and do some testing to make sure everything was working.
We modified many aspects of the original design as we progressed. Initially implementing an array of skin sensors to detect movement across the neck, we opted for a single accelerometer since it would be more comfortable and affordable. We initially used a bone conduction microphone, but these were unavailable commercially. But we used an electric microphone which utilizes similar power requirements in an analog signal. In lieu of our original microcontroller, a fan-style NRF chip, we utilized an ESP32 microcontroller. This was because the fan-style only supported Bluetooth Low Energy, which does not support the necessary audio streaming functionality. We also reduced our initial operating voltage from 9 volts to 3.2 volts using two AA batteries in series because the ESP32 power consumption could only handle 3.3 volts, and a voltage regulator circuit would cause the 9-volt battery to discharge faster. The finalized 3D model is pictured here and is being printed at the moment of recording this video. There were many iterations of the model that had to be redesigned due to flaws that caused the model to become unprintable. We were able to recover some print attempts to help in finalizing the size of the device.
Here we have our hardware functional block diagram, which was the early basis of our project design plan. This shows how we intended for the device to operate physically, with all possible and necessary components considered when organizing the diagram flow. We included a power supply, the existing buzzing motor component, and related inputs and processes such as speaking. We then added the sensor automation component, microcontroller, audio input, and a Bluetooth modules, all of which could be researched and decided on after initial planning. With our design planned in diagram form, we selected the best components for our project. Here we have the electret microphone, a capacitive transducer that uses low power and included an onboard op-amp to boost the audio signal before processing. To the right we have the signal processor, the SSM2167. This integrated circuit was ideal for taking care of all the audio mixing components, such as filtering or equalizing, compression, and noise gating. The sensor we selected for motion detection came to be an accelerometer, specifically the MXA2500EL, as it read accurate motion and also resulted in a more comfortable wearing experience of the device. On the bottom left we have the motor component that is used in the existing Electrolarynx module. We also have the microcontroller selected, which is the ESP32 module, with 30 pins, Bluetooth Classic capabilities, PWM and AGC modules integrated, and many analog inputs to use with our peripheral components. Finally, we have the power supply, which is simply the lithium iron phosphate 3.2 volt batteries, used in series to be able to power both the microcontroller and the motor circuit. All of our hardware schematic sketches consolidated into one picture. You can see where each component inputs and outputs each signal between each other. The top left is the ESP32. The top right we have the breakout board schematic of the electric microphone, and the output of this is directly input into the signal processor right below said sketch. Next we have the accelerometer and the motor, which both have inputs and outputs directly into the microcontroller, where the software does all the work for these modules. At the bottom we have our simple power supply circuit, which applies signal filtering, noise gating, and signal compression to improve the quality of the analog audio signal.
Moving on from hardware, we have the software flow diagram, which we developed early in our design process. This visual representation shows the basic functionality of the software included in our design. The state diagram at the top shows how a loop will read the sensor input to constantly determine if the buzzing motor should be on or off. The next state diagram shows the signal flow of the audio from microphone to Bluetooth transmitter, which includes device pairing and audio recording states. So, the accelerometer outputs two analog signals for the Y and X axis, and these are input to the microcontroller ADC module. When motion is determined based on sensor conditions, a PWM signal is sent to the motor. The motor volume is altered with the duty cycle of the PWM and the pitch by the frequency, both of which are changed using potentiometer knobs. For the audio analog signal, the I2S bus was set up to receive the audio input and convert it to digital. This signal serves as the Bluetooth A2DP source data. A2DP stands for Advanced Audio Distribution Profile, which is a Bluetooth profile designed specifically for audio transmission. Here is our prototype build on a breadboard circuit. Currently, we are waiting for our device housing to be printed. Once we have the housing, we will be cutting holes for the peripherals and joining the housing together using screws.
The finalized cost of our project design was roughly $163. Here is an itemized list. This project was not without its challenges and setbacks. One major ongoing issue is with the 3D printing of our device casing, which has been delayed multiple times due to design flaws and printing errors beyond our control. Another major issue was the initial microcontroller we had selected. We originally purchased and began development of our project on a Fanstel BT840E, but we later discovered that this module only supported Bluetooth Low Energy and not the Bluetooth Classic that would be necessary for audio transmission. From these setbacks and many other small bumps in the road, we learned some lessons. Firstly, feedback from the sponsors' needs and teammates allowed us to improve our communication standards and practices. We also learned to be agile with scheduling, as small issues could disrupt long-term timing of the project development, and flexibility and recoverability were a key to staying on track. This also relates to the importance learned of proactive planning and designing, where we now anticipate challenges and possible ways to avoid, troubleshoot, and learn from each mistake.
Matthew here. As project manager, I was in charge of scheduling, component soldering, sensor calibration, sensor and motor software, breadboard implementation and debugging, and power supply testing.
As project documenter, Juan Gomez was responsible for block diagrams and digital media, task breakdown and organization, Bluetooth profile setup, audio input, specifically I2S setup, and hardware schematic design.
As project liaison, Christian was in charge of project communication with sponsor, 3D modeling, casing design and printing, power circuit design, project budgeting, and bill of materials.
Here's our project poster, which summarizes all of the information we have presented here into a digestible 3x4 print. This also helps to reiterate and visualize our overall design and important descriptions.
Alright, so here's a demo of the volume and pitch of the motor. When the sensors are deviate too far from the original position, it activates the motor. And then, using the potentiometers, you can change the pitch. And then the volume.